Discuss that part. First, you need to understand what is your capacitors in series and parallel. Okay, so you need to understand your capacitors in series and parallel. Now, coming to your series and parallel part. Okay, so I told you in the previous class, whenever you apply some potential difference, what happens is your charge will get deposited onto the plates of capacitor. Basically, few of the electrons are removed from one plate and they are placed upon another plate. Now here, if you take a capacitor C1, one more capacitor C2 and one more capacitor C3 like this, if they are connected in series. Okay, so now here what happens is, first we will see only this series part. Okay, then we'll move ahead to parallel part. So now when capacitors are connected in series like this, I want you to keep an important point in mind. Now if you consider a dotted line between the plates of capacitor like this, inside these plates your enclosed charge is equal to 0. Here, okay, whatever happens here, this enclosed charge is supposed to be 0, because this two plates, like if you assume this to be some A and this plate to be B, those two plates A and B, they are not connected to any external circuit. So because they are not connected to external circuit, what happens is, okay, because they are not connected to external circuit, what happens is there will be no charge coming from any external point into these plates. As a result, your Q enclosed is going to be 0. Similarly, okay, in a similar way, if you take a loop here also, okay, you will have your Q enclosed is equal to 0 even here. So as a result, what happens is, for that Q enclosed to be 0, if one side, if the charge is plus Q, if this is plus Q, okay, or if this is first charge, if it is plus Q minus Q, this will become plus Q, this will become minus Q, this will become plus Q, this will become minus Q. So my point is, like how you have same current for resistors, here what will you have is, okay, Q remains same for capacitors in series. Okay, your charge remains same. Okay, that is your first point. Next, your second point is, okay, your charge is going to remain same for capacitors in series. Now coming to your second point, your potential difference will get divided. Okay, your potential difference gets divided. Now if you mark this as, okay, point A, point B, point C, point D here, now your potential difference is VA minus VB is equal to, okay, you can write Q, potential difference is Q by C. So that will become Q by C1 for the first part. Potential difference between B and C is given by Q by C2. Potential difference between C and D is given by Q by C3. Now if you replace this with a single capacitor, that single capacitor from here to here should give you a potential difference. Okay, so plus Vc minus Vc, plus Vb minus Vb, so your single capacitor's potential difference is, okay, your Q by C equivalent, that is equal to Q by C1 plus Q by C2 plus Q by C3 plus Q by C4. As a result, your equivalent capacitance is 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 plus so on like this. So this is going to your equivalent capacitance in series. Okay, now this result is exactly, Okay, reverse case of resistors. In resistors, if they are in series, our R equivalent is R1 plus R2 plus R3, and in parallel it is 1 by R equivalent is 1 by R1 plus 1 by R2. But here for capacitors it is exactly opposite. Okay, so remember that box thing. Whatever happens, your Q enclosed is supposed to be 0. So that is why your capacitors connected in series will have same charge. Okay, right? Next, I am moving ahead. Now, coming to the second case, for capacitors in parallel, if you have your capacitors in parallel, okay, so if you have your capacitors connected in parallel, this is C1, this is C2, this is C3, this is C4, like this. Now, when the capacitors are connected in parallel, what is going to happen is, okay, your cell of EMF E, okay, if you are connecting, how much charge is being drawn from here? If it is Q1, here if it is Q2, here if it is Q3, then what happens is, okay, this your equivalent capacitor, okay, or if you are replacing all these capacitors with a single capacitor, this single equivalent capacitor should carry a total charge, how much that is being drawn by all these capacitors together. So here what happens is, in parallel, okay, what is going to happen is, like how current gets divided for capacitors, charge gets divided. Okay, in capacitors charge gets divided, that is first thing. And your second thing is, okay, your potential difference will remain same. Potential difference will remain same. Your total charge is equal to Q1 plus Q2 plus Q3 plus so on, like this. Now, what is Q total means? It is C equivalent into potential difference that you apply between these 2 points. Okay, so that is equal to Q1, that is C1 into delta V, plus Q2 C2 into delta V, plus Q3 C3 into delta V, plus so on. So that will give you C equivalent is C1 plus C2 plus C3 plus so on, like this. Okay, so in parallel you are getting the sum of capacitances. In series you are getting sum of reciprocal of capacitances. Okay, so like this you will have simple questions based on the capacitors part, so you can do it. Okay, so now based on this you will have basic questions. So what are the basic questions? I will tell you. Now if you have two capacitors C1 and C2 like this, between A and B, what is the equivalent capacitance means? Your answer is going to be C equivalent is equal to C1 C2 by C1 plus C2. You should not write R1 plus R2. Okay, in parallel it is reciprocal. Actually it comes from this 1 by C equivalent is 1 by C1 plus 1 by C2. If you simplify this, you are going to get this. Okay, next, coming to the second part. Okay, so if you have a capacitor C1, if you have one more capacitor C2, okay, so if they are connected in parallel like this, what is your C equivalent means? In parallel I told you it is just simply sum of these two capacitances, which is C1 plus C2. Okay, now similarly if you have, okay, a group of capacitors, okay, some big capacitors are there. Okay, for example you have a 12C here, then some 8C, some 4C, then followed by 12C, followed by 16C, something like this, and then let us say this is connected to some other 2C, and then it is connected like this. And if you are asked equivalent capacitance, now similarly how you have done for resistors, all these three are in parallel. So many people will forget to do the reciprocal. So your C1 equivalent is 1 by 8C plus 1 by 4C plus 1 by 2C like this. then calculate equivalent of these two, then resultant of these two you combine, and whatever this part and this resultant of these two you combine and then calculate the equivalent. Now based on this you will have questions, okay, in the books, so you can do those. Okay, now I want you to watch this video and do all these questions. Now coming to the next scenario. Okay, so similarly how you have for resistors, here also you will have infinite grid of capacitors. So in infinite grid of capacitors, okay, in infinite grid of capacitors, that means very many capacitors are connected. So here also your same logic, okay, sum of n terms you can replace with n into n plus 1 by 2. Sum of n square terms you can replace it with n into n plus 1 into 2n plus 1 by 6. Sigma of n cube is n square into n plus 1 whole square by 4. Like this you can take sum of terms for the based on whatever terms you get in common. Arithmetic progression, geometric progression and all you can do it. Now I told you for infinite grid of resistors when they are connected, okay, what is that we are doing is previously, okay, if you have an infinite grid of resistors like this, some R1, R2 like this, if this unit is repeating, this part we have assumed it to be X, and then R1, R2, whatever term is repeating, we are replacing it with X, and then your equivalent of these two is, okay, your equivalent of these two is R2 into X by R2 plus X, and this are in series, you are adding up and equating it to X and we are solving for X. So exactly same thing, okay, we are going to do here, but we will slightly modify and then do it. So what is that we will do here is, if you have an infinite ladder network of capacitors like this, C1, C2 like this, okay, exactly in a similar way we will do it, but here your definition of series and parallel will be different. So this is C1, this is C2, and let us say the circuit is repeating like this up to infinity, and you are supposed to calculate equivalent capacitance. Now what happens is, okay, so if you assume this part to be X, okay, let C equivalent is equal to X. Now so if that equivalent is X, that repeating part we can replace it with X. So that gives you C1, C2, and then followed by you have equivalent capacitance of X like this. Now these two are in parallel, so this circuit will become C1. Because these two are in parallel, it is C2 plus X. Okay, now these two are in series, so C1 C2 by C1 plus C2. So that will give you C1 C2 plus X by C1 plus C2 plus X is equal to X. So solve for X from this equation, you will get the equivalent capacitance. Okay, now till here you have, okay, first three examples, do that. Okay, first three examples you do it, okay, based on this condition. Okay, now I will continue further. Okay, first three examples, then remaining part separately I will tell you. Okay, after third example, now next you can also do questions related to concept of potential. Okay, you can also do your apply your concept of potential related questions. So what is that is, if you have a capacitor C like this, okay, and one more capacitor, let us say it is 3C. So all that previously what all you have done for resistors you can do here. So this part if it is A, this part if it is 9C, okay, this part, just hold on, so this part if it is some 6C, this part if it is 18C, Okay, now if you connect it like this, okay, if you connect these resistors and this part if it is 2C like this, now what exactly happens is, okay, if you mark the potentials here, okay, this is V1 or VA, this is VB. Now this between A and B you have, if I try to redraw the diagram, between A and B you have a capacitor C. Now in between you have 6C and this capacitor, it is given as 3C in the question. So this will become 3C, 6C like this, then followed by 9C, 18C like this, then followed by 2C like this. So this is your equivalent diagram. Now calculate and simplify. So obviously all these two are in series, these two are in series, replace, and all the remaining 4 are parallel. So like how you are doing this potential idea for resistors, exactly the same you are supposed to do it. You do example 8 based on these questions. Okay, based on this idea do example 8 then followed by 9. Okay, and Wheatstone bridge also exactly same condition. So previously you have R1 R2 equal to R3 R4, no, so do the same for capacitors as well. If you have C1 and another capacitor here C2, and in between there is some other capacitor C5, and let us say you have capacitor C3 and C4 like this. Now my point is, if C1 by C2 is equal to C3 by C4, then we can remove middle capacitor. Okay, we can remove middle capacitor. So if you are removing this middle capacitor, this part will cancel off. So you are going to get your circuit as this part is C1, this part is C3, and this part is C2, this part is C4. Okay, so based on this also you will have simple questions. Now these two are in series, these two are in series, resultant is parallel with this. Okay, so based on Wheatstone bridge you have example 10. Okay, so do example 10. Okay, and regarding symmetry part, do not do it, do only till here. Okay, symmetry part and all I will discuss separately because that requires some decent amount of explanation. Okay, now do these basic questions. Then coming to the next part, okay, your next part is, okay, identifying capacitors when questions are given in terms of plates. Now in electrostatics, okay, in electrostatics, if you remember previously, if you have a charged plate configuration like this, okay, Q1, Q2, Q3 like this, if I ask you what is the final charge capacitor arrangement, final charges arrangement, you will write Q1 plus Q2 plus Q3 by 2 on leftmost plate and Q1 plus Q2 plus Q3 by 2 on rightmost plate. Okay, in this you will have plus x plus y minus y like this, so that sum of these two charges is equal to Q2. Once again, sum of these two charges is equal to Q1 and sum of these two charges will be Q3. Okay, so in middle you will have, okay, in middle you will have equal and opposite charges. In the middle you will have equal and opposite charges on capacitor plates. I mean in the metal plates that you have here. So now in the middle if you have equal and opposite charges, what happens is, okay, in the middle if you have equal and opposite charges, this region will form a capacitor, this region also will form a capacitor configuration. Okay, getting my point? So you have two equal and opposite charges and in between you have an insulating medium. So because of which you will have a capacitor configuration. So now if you have a insulating medium and a capacitor configuration like this, what is that we are going to conclude is, okay, two metal plates which are placed at some distance like this will form a capacitor configuration. So you have a capacitor in between these plates. Okay, now how this is related to what I am going to explain, I am explaining now. Observe carefully. Now let us say you have, okay, your question is like this. Let us say you have plates like this, 1, 2, let us say 3, let us say this is 4 plates like this. This is A, this is B, and these two are connected, and you are supposed to calculate, find CAB, your equivalent capacitance between A and B, where in which let us say they are placed, okay, equal distance is D, area here is A. So your capacitance of single is, okay, A epsilon naught by D is your capacitance for one capacitor here. There is a capacitor here, there is a capacitor here, there is a capacitor like this. Okay, now these capacitors, they are not in series or parallel. You cannot just directly by looking at it, you cannot say they are in series or parallel. Okay, so now if you are given questions related to plates like this, then what is that you are supposed to do is, okay, I'll give you steps, okay, for these kind of questions how you are supposed to do it, I'll tell you. But remember here totally how many capacitors are there means, if you look at this figure carefully, okay, this is one upper, okay, then this is one lower, sorry, one lower is here, okay, I am marking each side, okay, this is not one lower. So one upper, one lower is one thing, two upper, two lower is one thing, three upper, three lower, and four upper, four lower. Now here you will have how many capacitors means, you have totally three capacitors. Okay, what are those three capacitors? I will tell you. One lower, two upper is forming a capacitor configuration because there are two metal plates placed at some distance like this. So when two metal plates are placed at some distance like this, obviously what is going to happen is you will have, okay, equal and opposite charges when you are supplying this potential difference. So when you are supplying some potential difference like this, if you have equal and opposite charge, what is going to happen is, okay, you are going to have, okay, a capacitor configuration here, you are going to have a capacitor configuration, you are going to have a capacitor configuration. Now what are the possibilities for these three capacitors means, how many possibilities are there, I will tell you. All these three could be in series, okay, now two could be in series and resultant could be in parallel like this, or you can have C1 C3 in series and C2 in parallel like this, or you can have C2 C3 in parallel with C1 like this, or all the three parallel. Lot of possibilities are there for this configuration. Now for out of these different possibilities, which possibility is there, which possibility is correct, I am going to explain that. Okay, I want you to observe carefully. Okay, first of all, get convinced with the fact that I have told you very clearly that if you have two metal plates, okay, we have studied in electrostatics that if you have two metal plates placed at some distance like this, there will be some, okay, capacitor configuration. So now what is that I am going to do is, okay, I am going to draw an equivalent diagram. So first I want capacitance between A and B. So I will mark points A and B like this. Okay, don't worry, I will give these steps. So now A will form a capacitor with, okay, with A and B directly there is a capacitor. Okay, between A and B there is a capacitor. Okay, that is A is nothing but 2 lower, your B is 3 upper. Okay, 2 lower and 3 upper will have a capacitor directly connected like this. Okay, now coming to the next part, okay, there is a capacitor between A and B directly like this. Now your A is also connected to 2 upper like this, and this 2 upper is connected to 1 lower, and 1 lower and 4 upper are at same potential. Your 4 lower will form a capacitor with 3 lower. Okay, 4 upper will form a capacitor with 3 lower. Now if you observe carefully, there is a yellow color wire, so this blue color shaded portion is a wire. So what will that do is, that will form same potentials with plate 1 and plate 4. Plate 1 and 4 are supposed to be at same potential, so that is why I am connecting them. Okay, so now what is your equivalent capacitance means, this is C. So you have a capacitor C here. In the denominator part it is C1 C2 by C1 plus C2. If you do, you will get C by 2. Now once again these two are in parallel, so your answer is C plus C by 2. Okay, your answer is C plus C by 2, that will give you 3C by 2 is your equivalent capacitance. Okay, now I hope you have understood what I have explained. I will give the steps, don't worry how you are doing it, but first I will re-explain, just concentrate. Okay, so here what is my point is, okay, so first I want you to, okay, number the plates. Okay, whenever you are given a question, number the plates like that. Okay, 1 upper, 1 lower, 2 upper, 2 lower, 3 upper, 3 lower. From electrostatics, okay, from electrostatics, we do know the fact that, okay, we do know the fact that your capacitor configuration is formed in between the plates, because in between the plates you will have equal and opposite charges. So you will have equal and opposite charges on the in between the plates. So you will have such a configuration like this. Now once you get it, okay, after you number the plates, mark points A and B. Okay, you have to mark points A and B. Then start writing the plates with numbers. Okay, what is 2 lower, 2 upper and all, you look at it, and then you form the capacitor configuration like this. And remember, if you have a wire like that, all those points which are connected by the wire will have equipotential. That means they will be same potential, they will be connected to each other. Okay, so based on that I will give the steps. So for these kind of questions, what are the steps I will tell you. Okay, now point number 1. Okay, first number the plates of question asked, number the plates of question asked on upper side and lower side. Okay, on upper side and lower side. Okay, right. Next, number 2, once you have numbered, look for wires connected to plates. Okay, wires connected to plates. Once you look for the wires connected to the plates, okay, from this you remember the fact that, all plates connected to wire have same potential. Okay, all the plates connected to wire have same potential. Okay, that means they are connected to same point indirectly. Okay, next, then mark points A and B, and then with okay, detailed marking, form capacitor configuration, and calculate your equivalent and, okay, whatever is asked. Okay, so now hope you have understood it. Take the screenshot of this. Now based on this, okay, if I give you one more question, for example, let us say you have, okay, out of this one of the questions is wrong, I don't know which question it is, but one question is not given properly, I think the second one in your book. So this is A and this is B, answer figure was different, question figure was different, you correct it later. So now in this question, if I ask you what is the equivalent capacitance, this is 1 upper, 1 lower, 2 upper, 2 lower, 3 upper, 3 lower, 4 upper, 4 lower. Now between A and B there is no direct capacitor. So A will have 2 upper, A will have 2 lower. Now 2 upper will form a capacitor with 1 lower. 1 lower is connected to, okay, 1 lower is connected to 3 lower, okay. 1 lower is connected to 3 lower. 3 lower will form a capacitor with 4 upper. So you will get like this, okay. Once again, 2 upper will form capacitor with 1 lower. 1 lower is connected to 3 lower because 1 lower and 3 lower are connected to same line, same wire. So 1 lower and 3 lower are at same potential. 3 lower will form a capacitor with B. So that is why you are marking it as B. Now coming to 2 lower, 2 lower will form a capacitor with 3 upper, okay, and your 3 upper is not doing anything with B, okay. 3 upper has nothing to do with B. So in this case, okay, you don't have a capacitor configuration attached to this. So it is not forming any potential, okay, because your 3 upper, it is connected to 3 upper and 3 lower are connected to same point, okay. So they are connected to same point. So 3 upper and 3 lower I can connect. So if you observe carefully here, okay, your 2 lower, okay, 1 lower, 2 lower and, okay, sorry, 1 lower, 3 lower and 2 upper all are connected to same potential. So observe this, all are connected to same wire like this, all are at same potential. So this is your same potential wire, you can assume. Now what is your equivalent capacitance means? In this case you have C here, you have C here, and then they are connected to one more capacitor C like this. So you can calculate the equivalent and then simplify it accordingly, okay. So like this you have your example 4, okay. Number the plates, try to draw equivalent diagram, okay. So now this chapter is completely related to current electricity only except this part. Remaining part is dielectrics. I will talk about it in the next class, okay. So today I have some kind of webinar kind of stuff. I need to attend it from 7 to 8. So to attend that webinar, I am planning to give this as your homework. So watch this video, do that homework, okay. What are all the examples, you just simply do it. I am uploading this video into the YouTube part.